Wow, I had not expected to see this many people. I actually thought I was presenting over at track 4, and there was like no one there. I was like, oh, they're all hungover. It's fine. Oh well, thank you so much for coming. My name is Alexander Birke, and I'm going to talk a bit about procedural meshes in Unity. So a little bit about me. I am originally from Denmark, and that means I actually got into Unity early, back when it was primarily used in Scandinavia. I've actually been living in the UK for about 3 years. And last year I took the plunge and started my own game studio, where I'm doing my first game that uses a lot of procedural meshes. And I'm going to show you some examples from that today as well. How many in here are programmers? A fair amount, okay. How many of you learned to program like this? A fair amount, okay. I guess it's like I learned to program before Unity and all these like visual tools had made an impasse. So I learned it like through command line and like with C++ and that sort of thing, and it was quite like gratifying, but I was always like really interested in like having something like visual appear on the screen. So I think that's one of the reasons why I got into Unity as soon as I did. One thing though, I realized is if you're doing like just a standard Unity where you have like models that are made outside the engine, it's sort of like having a set of building blocks. Like you can only make like so many combinations with it. Like you can still make like something that's really like good and amazing. But if you want something that, for example, looks more organic, then you have to like go to procedural meshes. And I compare that sort of like to like having clay. When you like start to get how to do meshes yourself with code, it's sort of like it just opens up a whole new world of possibilities. That said, it's this weird clay that is like made out of numbers, so you do have to like understand a fair bit of math in order to make it work, but it's totally worth it. So here's what I'm going to talk about today. I'm first going to give you like some concrete examples of why you should learn to do procedural meshes. I'm then going to go over all the basics. So even if you've never like done, even if you don't know how a mesh actually works, you're going to get to understand that. I'm then going to go over some cool things I've used them for, and I'm also going to give you some tips on optimization. And especially the last part, if you have already done procedural meshes before, I think there's going to be something for you there, because it's actually quite hard to like find some of this stuff out. And sometimes the Unity documentation also, although it's one of the best documentations I've ever read, there's sometimes that it's a bit vague in why you should do one call instead of another. This talk is going to be fairly math heavy, or at least I'm going to like say words like vector and stuff like that. And my expectation is that you already know what that is. If you don't, I really recommend this book. It's one of the best math books out there. A lot of like the textbooks, they tend to be like really long, and there's a lot of like filler. This book is like really concise, and it basically covers whatever math you could ever possibly need in the game. It even explains shader programming better than the OpenGL book I had back at university. So I recommend that. I have also prepared a bunch of different repositories for you. So Unity already have a procedural mesh example on the asset store. Thing is, though, it starts off like quite high level. It sort of like already expects you to know how a mesh works. So I have made my own repository with like some really basic starter examples, which is what I'm using in this talk. So I'd recommend you first have a look at that and then go over to Unity's examples. I also have ported a library called triangle.net to Unity. When I say port, it was basically that I did a find replace on everywhere where that library uses doubles to floats, because we don't need all that precision. And that's used for something called Delaunay Triangulation, which might be valuable for you to have as a thing you can use. Right. So what can you use procedural meshes for? Well, I see like 3 major categories. The first one is player-made content. And I think Spore is a really good example of that. Like you have these like basic shapes and tools for players to basically create their own creatures. And without having like procedural meshes, you wouldn't be able to get these like smoother looking surfaces that you have in Spore. It also allows unique mechanics. Gish is by now a fairly old game, but it's really great. You play as this like tar ball, and you can either be heavy, sticky, or slippery, or a combination of those. And it has like this like great physicality to it because you are moving as if you were like this like blob of goo. So jumping is, I don't know, it feels like you're like sort of like really defying gravity when you do it, but it feels really gratifying. And of course, there's also the possibility of using meshes, procedural meshes for procedural generation of levels. I guess there's quite a lot of you interested in that. Like hands up if that's something you're interested in. Quite a few. I'm going to go a bit more into that later. And a good example of that, if you ever want to like get inspired, is to play Sir, You're Being Hunted, which is the robot has taken over and are hunting you as if it was like fox hunting simulator. It's quite British and really cool. Tilt brush. I guess a lot of you have heard about that. I didn't actually know that was made in Unity until a couple of weeks ago, and I think this is also really showcasing like what you can do if you have like access to actually creating your own meshes. Like anything that can be used to like make like freaking dragons is cool in my book. All right, so let's go over the basics. If you have a mesh, the basic building blocks are vertices, which are points in 3D space. And they need to be connected to each other in order to like form surfaces. On modern GPUs, that's always triangles underneath, because that's what it can rasterize, that's what it can like put onto the screen. So whatever you do, you need to make sure that you are in the end like actually converting it down to triangles. Inside Unity, there's like this is the basic setup you need. It's you need first to have a mesh filter. That's what basically stores your mesh. Then you need to have some sort of renderer on it. I think right now the choices are either having a mesh renderer or a skinned mesh renderer. Skinned mesh renderer is if you're using bones in your mesh and you want to like animate it moving. And you also need a script that is modifying the mesh. In my examples, that script is always on the object itself, but of course, it doesn't have to be. So if you're doing like a big world, for example, with like lots of randomly procedurally generated things, there's no reason to have like the script for that on each thing. You can just have it stored in one place. And this is everything you need to do in order to create a mesh. You first define a mesh instance, and you then have to fill it with vertex data and triangles. And that's actually like the most basic thing you need to do. So what the triangle array is, it's basically indices into the vertex array, and it tells like the GPU like how to go from like point to point and what defines a triangle. It's often where like things go wrong when you're creating your own meshes. Like it's quite easy to like think of how to like where the points should be, but then connecting them up with triangles, that can be tricky. If you want to have your mesh react to lighting, you also need to give it normals. So a normal is basically it's a vector on a given surface that tells the lighting system what way it's oriented. You can actually get Unity to calculate that automatically, but if often when you are doing procedural meshes, you already have like a normal, so you might as well send that data in yourself. And you can see here we have one triangle, the red one, that doesn't have normals, whereas the green one have normals, and that's why it actually gets shaded as the light rotates around. Of course, you also have to put on a shader that is using lighting. Colors used to be the primary way of like basically adding colors to your mesh, but you could only do that on a per vertex basic. So It's not being used that much more, but it can be quite beneficial if you're doing like if you need to pass in like extra information to a mesh, or if you want to like use the same texture but have it look different on different instances. You can actually do that in two different ways. So this first one, I'm using floats, just like a standard color, but you can also use bytes, and in that case you have to use the color 32 struct instead. This is actually a lot faster because you only have 1 byte per color component, whereas in the other case you have a full float which is 4 bytes. So if you need like performance and you don't need like the added range, you might as well use bytes. I didn't actually know this. It's because Unity's examples I actually think uses the floats. The advantage is though that if you're using floats, you can actually go above 1 in any of the values. So you can send over like a bigger range if you need to do that. All right. So this is how meshes are usually colored these days, and that is by like basically wrapping a texture around it. And you do that by defining what's called the UVs. So each vertex, you basically to define like a 2D vector, a set of coordinates on where where that is placed on your texture, on your image, and that basically can be used to like wrap a texture around your object. So the way you do that is like this. Quite simple, really. There's a little bit more going on in this example because I'm actually using a procedurally generated texture with a bit of Perlin noise, which, yeah, Perlin noise is a really good building block for doing procedural things. So I have an example with that in my project as well. Yes. All right. So I'm going to spend a little bit more time talking about setting triangle indices because that's what I find is the most tricky part to do. And we can see already, like with something as simple as a plane, it actually gets quite tricky. I used to play drums as a kid, and I sort of see like the problems of doing triangle indices and like doing the rest of your data as it's a bit like having two different rhythms you have to like to do your things in. Especially here, like we like. The DPU always expects your data to come in like a one-dimensional arrays, but you're actually using that to represent like a three-dimensional object. In this case, it's just a two-dimensional object because it's a plane, but that's really where all this like where the trickiness of doing meshes yourself comes into play. So we can see here, for example, I'm generating like vertices in lines like this, but when I need to assign triangles, I need to go, like I'm at the current vertex, I then go 1 ahead to like go to the one in front of me. But in order to then get to the one to the left or right of me, I will actually have to go a full length of a full width of this plane into the like this one-dimensional array in order to get to that one. And that is it can be kind of tricky. So this is like a fairly simple example. This is probably the most complicated mesh I have made myself. This is hexes within hexes. That took a while to figure out how to do. And what I found out is that the best thing you can do is actually try and draw it out on paper first, because often, yeah, it's not something that is expressed nicely in code. Like this is a lot of individual cases, but I did actually find out by drawing it out on paper that it's sort of like it's always the same kind of structure. So the letters you see down here, that's actually where I know that okay, there's like this is the amount and sort of like frequency, the rhythm that the vertices come out in, and I could see that okay. I would then have like functions to basically generate the vertices for each, and I would then have functions that would be like triangulate from A to B and triangulate from B to C, for example. And that would make sure that I could sort of like keep each triangulation as a separate entity, and that way I was, yeah, it basically meant that I didn't have to like try and solve the triangulation of this thing in one go, but I could like split it up into like subtasks. But I only figured that out because I actually drew it out on paper first. All right, so this is some stuff I have used procedural meshes for. Why not make a world that can bend? So this is from a global game jam prototype a couple of years ago. I think the concept or like the theme was we don't see the world as it is, we see the world as we are, or something like that. And it gave us this idea of basically making a game where you change your perception of the world, like is it flat or is it round? And it gave us a lot of like really interesting gameplay. I hope I'll get some funding to actually make this the next game I work on. And the way that I'm doing this is by basically treating like a given vertex position as a set of polar coordinates. So the y value becomes like the distance from the center, of course. And then I'm using the x coordinate to basically be like an angle for how much it should be deformed into when it wraps. It's a little bit more complicated than that because I wanted to have like this really nice transition. So what I ended up doing was to basically have two Bezier curves act as the normal vectors or as the unit vectors of my world. And normally they are completely like straight, but because these are like Bezier vectors, I can actually I can bend them. And then I'm cheating, so the last like 10% of the transition, I'm interpolating from the last value I had from the Bezier curves because they don't match up like precisely because you can't represent a circle perfectly with the Bezier curves. So what I'm doing instead is, for that last bit, I'm actually doing a spherical interpolation from that and then to the absolute correct position that I've calculated. Right. So this is the current game I'm working on. It's called Laser Disco Defenders, and it's a self-inflicted procedural bullet hell inspired by disco and cheesy sci-fi movies of the 70s. I've never listened to so much disco and seen so many crappy movies since I started in this project. And it has this, like the core mechanic is that every shot you fire, it stays in the level. So basically, you're creating like a bullet hell for yourself. The more trigger happy you are. And this game is actually coming out on the PlayStation Vita first, and that means that I had to think a lot about optimization as I was making it. And one of the things that is done with actually, like I'll have a question for you. How much do you think is done with procedural meshes? Can we have a guess? Yeah? It's actually all of it. I'm using something called Text Mesh Pro for having all the text in the game, which is like an amazing plugin. If you're doing UI in Unity, you kind of need that to get like really good font rendering. I'm using Unity Sprite System, which is also creating a mesh in the background and then sending over to the GPU to be rendered. And the lasers, that's my own creation. So the way that works is that it's actually one big mesh that I recreate each frame. And a given laser beam is consisting of like a start point where that's like the round bit. There's like the middle section and then the end point. If the laser is bouncing, so it's actually consists of more than one segment, there'll also be like a flare around the hit point. And that's basically, it serves two purposes. I found out through playtesting that people had a hard time like hitting stuff. So by having that flare and doing hit detection, that suddenly it became a lot easier. And it also hides the janky intersection between the two segments. So yeah, no reason to fix something if you can just like hide it. So on mobile platforms, which you can sort of like consider the Vita to be, doing deferred lighting, like having a lot of lights, are normally something you cannot do. Actually, every time you have a light source in Unity, and it's running in deferred mode, it's actually creating an extra draw call. So as you can see, I want to have all this like really nice lighting in my game because this is like laser beams, like and disco. It needs to like lit up the environment. So what I ended up doing is actually write my own lighting system, where I get, I don't know how many lights I can have, like probably 100 on a screen at a time in one draw call. And the way I do that is by actually generating a mesh, which is sort of like stamping light or like just a texture into a buffer. So basically, I first go over all the lasers in my scene, and I then draw them again. But I stretch them out, and I use another texture, which is like more has like a softer fallout. And I can also put in like other light sources. Right now, the only one I have is like a circle light, which is what I use on characters and enemies and so on. But if I wanted to, I could basically take whatever texture and just create a quad, a rectangle with that, and actually have it be rendered in. Another cool thing I realized is because I don't have any, like, there's nothing in the game that obscures the light, and because everything is just like this diffuse fall-off, I can actually get away with using a really, really low-res buffer for this. So this is automatically set to be 10% of the current screen resolution. And you can actually see it because of the way that the game looks already. So that means that I get like lighting that looks really good, really cheap. And an added benefit is also that, and we can see that if I go back to this GIF, I can actually make long lights. And that's not something you can do with the built-in system in Unity. All right, so I am also doing procedural levels, and I don't know if there's any games that have done this before, but I'm actually using polygons as my like basic building block, and I then combine that into one big polygon that then forms the outline of my level. And that has the benefit that it's actually really, really fast to generate. Like I think it takes around, yeah, maybe like 100 milliseconds at most on the PlayStation Vita. So you can probably generate like 1,000 levels in a second on PC or something like that. And that's how it looks like when it's combined, of course. So the trick is, though, I have to separate this out. So I have like a foreground and I have a background. And I need to create, like, the background is easy. That's just one big square. So I'm just doing that by like, yeah, simple maths. But creating this like like foreground mesh is a lot harder to do. And how am I doing it? I'm actually cheating quite a lot. So I'm using something called Delaunay Triangulation. That's where triangle.net I talked about earlier comes into play. This is basically a technique that was developed for physics simulation. So they would have like a numerical method for like calculating something, but it would only work in triangles, and they would then have like a lot of data points, and they would then need to like quickly create a triangulation and a good triangulation for that. And what is a good triangulation? That basically means that you have you avoid to have like narrow triangles, because that's actually something that can lead to problems in most simulations. And on the GPU side, it's also a good idea to avoid it because of rendering artifacts. Runtime-wise, it can be a bit slow. So I wouldn't do it every frame, but I'm only doing it like when I create a new level, so it works quite well for me. And I have released the code for this on GitHub, if that's something that could be of benefit to you. All right. So here's where you get all like the secret knowledge I have gained over the years. It basically goes from, yeah, you should definitely do this, and it's easy to like do, to, okay, you're really looking to like get squeeze the last performance out of your game, then you should maybe try and do this. So if you need to debug, like, you're dealing with something that's visual inherently. So if it's not showing up, then it can like, you could try and like just use like console output or like breakpoints, but quite often that's like the worst way of actually trying to understand what's going on. So I really recommend using the Gizmos class or the debug class in order to draw stuff out. Also, try and rotate your camera. Like the mistake I have made the most times is that I have assigned my triangles, and the triangles are perfect, but they're pointing the wrong way, away from the camera. Basically, like when you define the triangles, you define like an order then, and if that's the wrong way around, the GPU won't render them. Basically, it's an optimization. There's no reason to render the inside of something if it can't be seen. So yeah, that happens quite a lot. And of course, you can also try and turn on wireframe rendering, which can also help. All right. So in order to optimize static meshes, there's a bunch of different things you can do. It's really, if you're ever doing a talk at Unite or at anything else, try and show it to someone who actually like works with the technology, because they might point something out. I didn't actually know this, but mesh.optimize does absolutely nothing. There's nothing happening when you call that. It used to do something like 2 years ago, but nowadays it doesn't. So in some ways, this is actually good, because it means that you are in charge of creating your mesh as optimized as possible. What that means is that you need to make sure that your vertices are as like coherent as possible. There's something called cache coherence, which is terminal optimization, and it basically means that if you have something that are used together, it needs to also be together in memory. Otherwise, you're going to have like more memory reads, and that's going to make it slower. So in reality, though, like most of the time, you are going to create your mesh in that way, because it just makes the most sense that, well, if I'm here and I'm like generating vertices, there's no point of me to like go over here and generate some vertices and then go back here. So, but it's still like nice to keep that in mind. You can also use static batching utility to basically take like a bunch of meshes you have created on the fly and get them to render in one draw call on Unity side. Another thing you can do is also use, and they actually stay separate meshes that way, and you can actually turn them on and off even then, but they still render in one draw call, which is nice. You can also combine multiple meshes, which is another optimization technique that can be handy. It really depends on like the situation you're dealing with, what you should do. All right. So this is like what I have been doing the most on this project, is like getting my dynamic meshes, like all the lasers and all the lights, to be as quick as possible. The first thing you should do, and that's you basically get this for free, is to set your mesh to be dynamic, because it means that the graphics, the mesh API, the underlying graphics API is actually being told that I want to use a buffer, like a memory region on the GPU that is that I can update a lot and often. This is a bit interesting. I have asked people at Unity why this is faster, and they couldn't really answer it. But I found that if you double buffer the mesh component, you can actually get some more performance out, like 10, 15%. I think that's what I saw. At least I saw like a good bump in frame rate. It does mean that you use more memory, of course, because you have like 2 mesh objects floating around, like, and they each have like a copy of the mesh. But quite often that's worth it. Right. So you can actually assign data to your mesh instance in 2 different ways. You can either just say mesh.vertices, or you can say mesh.setVertices. And the setVertices actually takes a list in. And that's quite handy, because quite often when you're generating your mesh, you don't actually know in advance how many points and how many like UVs and colors you need. So I tend to use lists all the time. And I didn't actually know this, but if you have a list and you say to array, you actually create like a complete copy of the array. I thought in my naivety that you just got like the internal array inside the list object like sent out, but that doesn't happen. And what makes it even worse is that then inside the mesh API, it's actually taking another copy. So you're just copying stuff around without actually having to do it. So what you can do instead is using set vertices and equivalents for all the other kinds of data. And that way you can just send your list in and you avoid and yeah, to have like an extra copy happening. Another good optimization is if it's not on the screen, well, you probably don't have to draw it. So on Laserdisc Defenders, I'm using basic Frustum Culling for that. And you can see here I'm actually like enabling and disabling drawing lasers outside what the camera can currently see. And as you can see in the profiler, that gives me quite a lot of performance. And it's not something that has any impact on the game whatsoever. I would say, though, it's still nice that you can actually, as a debug option, like disable this culling, so you can actually see the mesh in your whole scene. If you're, for example, something is, for example, in my game, I could have like a laser colliding with something outside the screen before I can actually get around to see it. So it's really handy to be able to like have it disable that optimization. I can't actually read that slide, sorry. Oh yeah, this is another pretty cool trick. I haven't done this myself, but if you are, if you have like something, I think it was like a game called Robotech or something like that. I saw them do this, where they would, they had like a robot with a lot of like individual moving parts, and they needed it to move. So what he actually did was he created bones for that on the fly. So you could also accomplish that quite often by having that be like separate meshes, but then you would have like more draw calls. So what he did instead was that he would create it as one big mesh, but he would automatically skin it and make bones for it, and he could then move the bones and then get movement in really cheaply. So this is like we're getting into the territory of like things that are quite hard to do. The Unity API is not thread safe. That's something that a lot of us would like it to be because it would make life a lot easier. But when it comes to creating meshes, a lot of the time the only thing you're doing is actually just crunching numbers. And there's a good chance that that can actually be offloaded to a separate thread. So if you have like experience doing multithreaded programming, or if you're really chasing like that like last performance, that might be something that could be beneficial. This is like a slide from a profiling example of Laserdisc Defenders, and you can see all that stuff up there. That's where I'm just like generating meshes. So 2/3 of my execution frame is actually spent on that, and all the space down there, that's cores like CPU's cores doing nothing at all. So I might at some point actually get around to like stick it in a separate thread. But it's a bit tricky because you have to like merge back with the Unity main thread. But it is possible to do it. All right. There's also the possibility of not doing the mesh generation on the CPU at all, but actually doing everything on the GPU. And you can do that with compute shaders, which is basically general purpose shaders that you can basically make them do whatever you want. They are still like limited to a few platforms, and one of the reasons I use Unity is that I want my game to be as portable as possible. So, for example, starting to do something like this is not something I would necessarily do in a production-ready game. Maybe in a couple of years' time when it's like you can expect it to be available on most platforms. That's something I would start to look into. But it does yield a huge performance increase if you can do it the right way. And if you're only targeting these platforms with your game, well, give it a go. So that's the basic. That's my talk. I hope that I've given you a good example of a good understanding of all the different possibilities that procedural meshes open up, and also that paper is really useful. Like I see like a lot of programmers, they don't actually like they don't have like paper anymore. They just like everything is happening on the screen. But sometimes it's just a lot easier to just work with like an analog medium like that. I hope that I've also given you like a bunch of different ways that you can optimize your mesh. And yeah, I encourage you to try it out and have a lot of fun with it. Thank you so much.